In section 2.6, we will now take what we've learned about solving non-homogeneous linear differential equations with constant coefficients and apply it to a more complex mass spring system. We will study forced oscillations and resonance. The component that we are going to add to our mass spring system is the external driving force. Consider an external force, F of t, acting on a vibrating mass that causes the spring support to oscillate in simple harmonic motion. So let's consider our setup. We're going to start with a base, and to this base we'll attach a spring, and on the end of the spring we're going to hang a mass. We'll call that mass M. Previously, we had talked about plucking the spring and modeling its oscillation as a function of time. The change that we're now making to this experiment is we're going to allow the base also to oscillate. So we will have some sort of external harmonic oscillator that causes this base also to move up and down. So now our task is not only to model the natural oscillation of the mass on the spring, but also to account for the external driving force. Let F naught be the magnitude of the external force and omega the circular frequency of the external force. Now don't let that word circular affect the way you think about the problem. Circular frequency simply means it is associated with a harmonic oscillator, or the external forcing function will be modeled by a sine or a cosine wave. The coefficient of the argument will be omega. That's what we're referring to as the circular frequency, or the number of times per minute that base is going to oscillate up and down. Now, the differential equation of driven motion changes just a little bit. On the left side here, you see our familiar terms, mx double prime, that's mass times acceleration, plus damping constant c times x prime, that's velocity, plus k spring constant times x position. What's different about this differential equation of driven motion is this term over here on the right side. This function describes the external force acting on the base of our experiment here. This creates a non-homogeneous linear differential equation. Now, a little more detail to the functions that we're going to consider in this section. F of t will be modeled as a harmonic oscillator. Either initial force F naught times cosine of omega t, or F naught times sine of omega t. So as the mass oscillates up and down based on the natural physics of the spring, it will also experience further oscillations based on the external harmonic forcing function. So whereas the mass would normally oscillate up and down in natural behavior, of course absent damping forces, now it's going to experience oscillations upon oscillations as it also is affected by that external forcing function. So we will consider two cases. The first case is undamped forced oscillations, and then we will look at driven motion with damping. In the absence of damping, now remember, damping could be something such as a shock absorber. It could be programmed in as air resistance or friction, some sort of resistance to the velocity of that mass. In the absence of damping, a mass which experiences a harmonic external force, that's just a regular harmonic force moving the base of our setup up and down, will naturally oscillate according to the physics of the spring. In addition, the mass will experience further oscillations as caused by the external force. We will see this as oscillations upon oscillations in the graph of spring motion. So we want to begin by solving our problem in general. So the equation of motion is mx double prime plus kx equals, and we'll just use F naught cosine omega t for our external forcing function. Notice in this equation, the damping constant c is equal to 0. This simply means that we are looking at undamped oscillation, undamped motion. So no resistance to the velocity of that mass. Now, the presence of this term on the right side is why we classify this as driven motion. So the external harmonic oscillator will also affect the position of that mass. To solve this differential equation in general at first, let's go ahead and divide through by m. This is going to give us x double prime plus k over m times x equals f naught over m times cosine of omega t. As we did previously, let's define new parameter omega naught to represent the square root of k over m. Our differential equation then becomes x double prime plus omega naught squared x equals f naught over m cosine of omega t. So make sure you understand we have an omega naught and an omega in the same equation. Recognizing that this is a degree 2 linear, non-homogeneous differential equation, we first need to solve the associated homogeneous differential equation using the characteristic equation. Then we will find a particular term. So using the procedure that we have previously learned, let's look at our corresponding homogeneous differential equation. We're going to solve x double prime plus omega naught squared x equals 0. We do this by converting it to algebra, the characteristic equation. We have r squared plus omega naught squared equals 0. Solving for r, we would find r squared is negative omega naught squared, and taking the square root of both sides, we would end up with plus or minus omega naught I. So we have two complex conjugate pair solutions here. So our complementary term, we'll call it x sub c, can be expressed as, notice the real part is 0. Also observe that my independent variable here is t and my dependent variable is x. We've been using x as the independent variable. Now things are changing just a little bit. So we have e to the 0t times constant c1 times cosine. Now we're going to take the imaginary part, omega naught times t, or at least the imaginary coefficient, plus c sub 2 times sine of omega naught t. And let's go ahead and simplify that, recognizing that e to the 0t is 1. Then our complementary solution would simply be c1 cosine omega naught t plus c sub 2 sine of omega naught t. The next thing we need to do in our solution process here is to find our particular term, x sub p of t. And if you'll recall, we'll make an assumption for x sub p based on the nature of our non-homogeneous term. So we have a constant times cosine of t. So we're going to let x sub p equal a constant times cosine of the same multiple of t. Now, in general, if you'll recall, we want to make sure that we include all of the linearly independent terms that are included in our non-homogeneous term plus its derivatives, right? So in general, we would add a b sine of omega t over here. However, if you notice, since we are missing our middle term, x prime, we have the original function x and the second derivative. If I differentiate cosine, I'm going to get negative sine, but then if I find the second derivative, I'm back at a cosine wave. So this second term is not necessary since that x prime term is missing. If you programmed it here in the xp term, you would eventually find out that b equals 0. But in the absence of that x prime term, I can skip to the second derivative, which is again going to be a cosine wave. So let's find our first derivative. Xp prime is negative a omega cosine of omega t, and xp double prime then would be negative a, whoops, forgot my sign, cosine turns into sine for a derivative. Then we're going to end up with negative omega squared cosine of omega t. Let's take this information and substitute it into our differential equation. Starting with x double prime, we have negative a times omega squared cosine of omega t. Next, we have plus omega naught squared times x. That's a cosine of omega t equals f naught over m cosine of omega t. Now, there are quite a few parameters in this one equation, so stay focused on what we're looking at here, what we're attempting to find. This is the method of undetermined coefficients. I need to be able to determine the value of A so that I have the specific information for my particular term. So my goal here is to solve for A. On the left side, both of our terms contain cosine of omega t, so we can go ahead and factor that out. Also notice both of those terms contain an A, so I'm going to factor it like so. A is the greatest common factor. We have omega naught squared minus omega squared, whoops, not subscript, superscript there, times cosine of omega t. You can think of that as factoring out the greatest common factor, A times cosine of omega t. On this side, no change. We have F naught over M times cosine of omega t. Now, we're going to set our coefficients of the cosine function equal. Again, this is the method of undetermined coefficients. The coefficient of cosine on the left, if this is an identity equation, should be equal to coefficient of cosine on the right. Now we can go ahead and solve for A. A would be F naught divided by M times omega naught squared minus omega squared. Got an omega naught and an omega squared to keep track of here. So we have determined our undetermined coefficient, and we can say therefore the general solution x of t is equal to the complementary function. We found that previously, c1 cosine of omega naught t plus c2 sine of omega naught t plus, now we're going to add our particular term, A. We discovered A is F naught divided by M times omega naught squared minus omega squared times cosine of omega t. So what you want to recognize about A is it is simply a constant, but now it is in terms of the magnitude of our external forcing function, the mass, also omega naught, which is the square root of k over m, and omega, which is our external circular frequency of that harmonic oscillator. Because there was no damping that was programmed into our original equation of motion, if we think about the limit of x of t as t approaches infinity, it's going to continue oscillating indefinitely. Again, the reason for that is because we are looking at undamped driven motion here. Now, before you get too discouraged with all of those parameters, what you're going to find is when we actually have values in for all of those parameters, this process of solution is really pretty simple. Let's try example 1. Suppose an object with m equal 1, mass equal to 1, oscillates on a spring with spring constant k equals 4. We're keeping it really simple here, not even introducing units. Further, suppose the base of a spring is oscillating according to f of t equals 5 sine of 3t. Model this system with a differential equation. Find a particular solution subject to x of 0 equals x prime of 0 equals 0. Then examine the graph of the solution to understand the motion. So we need to model this situation with a differential equation. There is no damping constant, so we're looking at undamped motion, but because we do have an external force acting on our spring mass system, we call this driven motion. So this is undamped driven motion, or undamped forced oscillations. Our differential equation should look like mx double prime plus kx equals f of t. M in this case is given to be 1 and k is given to be 4. Our external forcing function is 5 sine of 3t. So it's a periodic, regular, external harmonic oscillator. So we can imagine again the base of our spring mass system oscillating, which affects the natural oscillation of the spring mass system. Let's work on the mathematics part, solving the differential equation. To solve the differential equation, the first thing that we need to do is to find the characteristic function. We're going to solve the corresponding homogeneous differential equation, x double prime plus 4x equals 0. We do that with the characteristic equation, r squared plus 4 equals 0. You're probably getting to the point where you can solve these differential equations in your mind by now. Looks like we have two complex conjugate roots. So our complementary function, x sub c of t, then, would be e to the 0t, which is 1. I'm just going to leave it off this time, times c1 cosine of 2t plus c2 sine of 2t. Now, if you're wondering where that's coming from, just let me remind you, the way that we express our general solution is dependent upon the nature of those roots. Are they real and distinct? Are they real and repeated? Are they complex conjugate pairs? That's indicating how we express that x sub c of t. So if you need to go back and review that, now would be a good time to do it. Once we find our complementary function, our next step is to find our particular term, and we're going to do so with the method of undetermined coefficients. You could also do this, by the way, with the variation of parameters method. Our external forcing function, our non-homogeneous term, is 5 sine of 3t. We're looking at the nature of that function and thinking about its derivatives. Like we did on our general solution, our general example above, we're going to look at x sub p being a multiple of sine of 3t. If we consider its derivative, its first derivative is cosine, is a cosine wave. However, once again, because the x prime term is skipped in this differential equation and we go straight to x double prime, this is an efficient assumption or a sufficient assumption for our x sub p term. No information more is necessary. xp prime then would be 3a cosine of 3t, and xp double prime would be negative 9a sine of 3t. So we're going to substitute this information into our differential equation that we see here. X double prime gets replaced with negative 9a sine of 3t plus 4x, that's going to be 4a sine of 3t, equals 5 sine of 3t. So both terms contain sine of 3t. Let's go ahead and combine those. We end up with negative 5a sine of 3t on the left, equal to 5 sine of 3t on the right. We can equate corresponding coefficients here, so it looks like a should be negative 1. So our particular term, x sub p of t then, is a negative 1 sine of 3t. So we will add this to our complementary function and express our general solution. We will obtain the function x of t equal to complementary function c sub 1 cosine of 2t plus c sub 2 sine of 2t plus x sub p, which is minus sine of 3t. Now, we're not going to stop with the general solution because if you'll recall, we were given a set of initial conditions. So let's go ahead while we're here and find the first derivative of x. So we'll be set up to plug in our initial conditions. So our first derivative here looks like negative 2 c sub 1 sine of 2t plus 2 c sub 2 cosine of 2t minus 3 cosine of 3t. Our first given initial condition was x of 0 equals 0. Let's go ahead and plug that into our function x. I'm going to set the function equal to 0, and we're going to plug 0 in for t. Cosine of 0 is equal to 1, so we're going to end up with c1, and then sine of 0 equals 0, so that's it. 0 equals c1. That one was pretty easy. Let's work on our second initial condition. The second one was also x prime of 0 equals 0. Let's go ahead and plug that into our first derivative. I'm going to set the first derivative equal to 0, and we're going to plug 0 in for t. Now recall, sine of 0 is 0, so that term goes away. Cosine of 0 is 1, so we have 2c2 minus 3. It looks like from this equation we can determine c2 equals 3/2. So let's refine our general solution and write it as a particular solution. We end up with x of t equals, now remember c sub 1 is 0, so we lose that whole entire first term. X of t equals 3/2 sine of 2t minus sine of 3t. That is our particular solution. That's our equation of motion. Now I've got a little bit of extra space here at the top of the next page. I'm going to rewrite the particular solution so that we can examine the graph and understand what's happening in this solution. So our particular solution that we found, once again, is x of t equals 3/2 sine of 2t minus sine of 3t. Let's take a closer look at the two terms of this particular solution so that we really understand what's affecting the motion of this mass. Now, the first term, the coefficient of t in the sine function is 2. That is our omega naught value. That, remember, was came from the root of our characteristic equation. We could use that number to find the period of this sine wave. This particular textbook represents period with capital letter T. You can also just write period there. The period of this sine wave would be 2 pi over 2, or pi units. This term describes the natural oscillation of the spring. In the absence of that external force, this term would be describing how the mass oscillates in the spring mass system. As for this second term, notice that the coefficient of t is 3. This is our omega value. So in this case, omega is 3. This is matching the external harmonic oscillator. If you'll think about our non-homogeneous term, its argument was also 3t. So this omega is matching the frequency of our external forcing function. Now, if we think about the period of this function, it would be 2 pi over 3, a little bit shorter. So this is due to the forced oscillation. It's going to interfere with the natural oscillation of the spring. So let's sketch a graph of the behavior of our spring. Recall here that our independent variable is t for time, and our dependent variable x is the position of that mass. Now, just as a reminder, we have a base with the spring attached to that base and a mass oscillating on the end of that spring. And we're allowing this base to undergo harmonic oscillation as well. So this is moving up and down as the spring naturally moves up and down according to its own physics. So the frequency of this forcing function is 3. The period here is 2 pi over 3. Whereas the frequency here is 2 with period pi. So again, in the absence of that external forcing function, this is how that spring would behave. It would just follow a sine wave moving up and down very smoothly. But because we do have that external forcing function, it will interfere with the smooth sine wave of that mass spring system. So to understand the graph, I'm going to use my graphing calculator. I'm going to go to y equals and type in our particular solution. I'm also going to make sure that my calculator is in radian mode, and an easy way to view a trig function is to do zoom number 7. That's zoom trig. When you do the zoom trig function, it will set your viewing window from negative 2 pi to positive 2 pi, and your y value from negative 4 to 4. Each unit on the x-axis is a multiple of pi over 2. So we're really just interested in the right side of this graph because we're looking at t representing time. So we'll start at t equals 0 and move to the right. Now you can see some resemblance of a sine wave every pi units there, but but it is, again, being interrupted by the interference of that external forcing function. So it almost looks like a heartbeat graph that you'd see in the hospital, but it is a sine wave with interference with its amplitude. So I'm going to adjust my window just a little bit so that we can make a good sketch of this graph by hand. I'm going to set the minimum value for x, which is going to be our t on our graph, to be 0. And let's look at 2 pi as our t maximum. So we'll look at the graph from 0 to 2 pi. Remembering that the period of the natural oscillation of the spring is pi, I can see some semblance of a sine wave from 0 to pi, although the amplitudes are not symmetric like they normally do. In the second fundamental cycle there, from pi to 2 pi, again, you can see a sine wave, but its amplitude is being interfered with. If we go back and look at our original forcing function, the external forcing function, notice it had an amplitude of 5. However, on our graph, it's never quite going to reach that amplitude. The spring and the external forcing function are working to cancel each other out in some respect, and so it looks like our maximum amplitude is somewhere between, let's see, 1, 2, 3, -4 and 4. So let's transfer this information to our graph by hand. I'm going to use the same multiple of pi over 2 to label my units here, just like the last graph that we looked at. And we'll have a maximum amplitude of 4. If we switch back over to our graph and take a look at the details, we're going to have a sine wave that starts out rather flat at first, reaches an amplitude just under 2, and then passes down to an amplitude of about -3, and then comes back to 0. So to sketch this out by hand, get some guidelines here. It's going to go something like this. Okay, and this is, of course, is an approximation. And then it's going to level back out. I do want to include an arrow on the end of my graph to show that this mass is going to oscillate in this respect indefinitely. We have that external forcing function interfering with the natural oscillation of the spring, but because there is no damping, this motion continues indefinitely. Undamped driven motion can lead to some really interesting results. We're going to consider 2 phenomena, the phenomenon of beats and pure resonance. If omega naught, now remember, omega naught is the frequency of the natural frequency of the spring, and omega matches the frequency of my external forcing function. If omega naught is very close to omega, but omega naught is not equal to omega. Now, this is a very relative expression here, very close to. That means they're very similar. The closer they are, the more we're going to experience what's called the phenomenon of beats. So if these 2 values are very close together, it can be shown, we're not going to show it here, but it's in full glorious detail on page 164 of your text, that the general solution is given by x of t equals, now what I want you to see here is we have a constant, those are all parameters, so that's a constant, times the product of 2 sine waves. So instead of adding and subtracting sinusoids here, we've got the product of 2 sine waves. One has coefficient here omega naught minus omega, and the other one is omega naught plus omega. In this case, the one with the larger coefficient here, right, omega naught plus omega is bigger than omega naught minus omega. The larger that coefficient, the smaller the period, right? So we could say that sine of 1/2 of omega naught plus omega t is a rapidly varying function. That is, it has a smaller period. Whereas sine of 1/2 of omega naught minus omega t is a slowly varying function. This number is smaller, which causes you to have a larger period. This leads to a very interesting graph. If I imagine, first of all, the sine wave with the larger period, okay, and I can see that here on the outline of this graph. If I imagine the sine wave with the larger period to have the amplitude of, remember the coefficient of your sine wave is the amplitude. Of course, we have this numerical coefficient here, but I can also think about this function as part of the amplitude of this slowly varying sine wave. Remember, we said this one is a rapidly varying function. So I can think about this sine wave having a rapidly varying amplitude. So the actual curve here is varying its amplitude within that larger sine wave. So you can think of it as a rapidly varying sine wave inside that larger sine wave. Okay, so it's a very interesting looking graph. Now, a rapid oscillation with a comparatively slowly varying periodic amplitude exhibits what we call the phenomenon of beats. Now, the reason we call it beats is because it is related to music. For example, if two horns are not exactly attuned to each other and simultaneously play their middle C, then one hears a beat, an audible variation in the amplitude of the combined sound. So if their notes are very close, but one is off tune just a little bit, and you listen to it, maybe you've done this with the piano. If you've ever tuned a piano, you play a tuning fork and you listen for variation in the sound. It sometimes sounds like a wah, 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 wah sound, or if you have two horns that you play together and they're off just a little bit, you can actually audibly detect the variation in that amplitude. So we call this the phenomenon of beats. So again, if the natural frequency is very close to but not the same as the external frequency, then you end up with what's called the phenomenon of beats. And that happens in music, and this would simply mean that your spring would oscillate something like this over and over and over. Another interesting result with undamped driven motion is called pure resonance. Remembering that to produce the phenomenon of beats, omega naught and omega have to be very close but distinct. That is not equal. What happens when the natural frequency of the spring and the external frequency match exactly? So we're going to consider what happens as omega naught approaches omega in our solution x of t. So here we have our general solution that we derived on the first page. It can be shown, that means we're not going to do it here, but it's outlined in your text on page 165. It can be shown that the particular term x sub p equals what we have here. Okay, so what I want you to see, just look at the overall big picture, the bird's eye view. We have a constant here composed of several parameters, and we have a sine wave. Let's think of the sine wave as having amplitude t. Remember, the coefficient of your sine wave indicates its amplitude, but here we have a variable amplitude, and in particular, it is a linearly increasing amplitude. So what happens is our sine wave will continue increasing its amplitude, getting bigger and bigger with each oscillation. This is what we call the phenomenon of resonance. Now, in this case, the amplitude is eventually going to increase without bounds. We may interpret this phenomenon as reinforcement of the natural vibrations of the system by externally impressed vibrations at the same frequency. So you can think of this as far as our spring mass system as the oscillation of the spring is in sync with the oscillation of the external forcing function. So as this external forcing function drives the mass down, the mass is also already in motion in the same direction. Okay, when our external forcing function moves up, then our mass moves up with it. Okay, so they're always in the same direction. So what's going to happen is that external forcing function is going to reinforce that mass each time because they're in the same direction, causing that amplitude to get larger and larger both times, or in both directions. Now, I think about this sometimes when my kiddos are jumping on the trampoline, right? They're all jumping up and down, but they play this game called Rocket when one lands just before the other one and goes down while the other one comes down, and they're in the same direction. They hit the base of their jump at the same time, but one jump reinforces the other and sends one of my kids way up into the air, and it makes me think about resonance. So think about resonance if you're ever playing Rocket on a trampoline. But in a more serious note, resonance basically is destructive to any mechanical system. So this is something that you want to watch for and avoid at all costs. One of our instructors in engineering at Amarillo College, who used to practice engineering professionally, said this happened in a simple air conditioning unit that they had installed in one of their buildings. There was a case of resonance. The pipes were oscillating at the same frequency as their forcing function, and it totally destroyed their system. And they understood that it was due to resonance. The frequencies were matching, reinforcing each other, destroying the mechanical system. Resonance explains the destruction of many things in history, such as bridges, airplane wings, and hotel floors. Your book has some interesting stories about buildings where people were dancing and the beat of their dance matched the natural oscillation of the floors of that building, and it caused the floors to collapse due to the phenomenon of resonance. Soldiers avoid this situation when they break cadence when marching across a bridge. Bridges, buildings, lots of physical structures have natural oscillations. The Tacoma Narrows Bridge, which collapsed many, many years ago, at first was blamed due to resonance. That is, the natural oscillation of the bridge happened to match the wind, and it caused it to resonate and crumble. However, with more careful detection, they understood that it wasn't exactly resonance, but it was something related to that. So this is a really interesting thing, also something that you want to be aware of and avoid at all costs in mechanical systems. So think about it on the trampoline. I also want to tell you a quick little story about beats. So when you're sitting at a stoplight, maybe you'll think about your differential equations teacher. We were talking about beats, how you have a rapidly oscillating function that varies according to a slower oscillating function. When I'm sitting at a red light, let's see if you notice this too. You're all math people. You probably think like this as well. Have you ever noticed if you're sitting behind someone whose blinker is on and it catches your eye and you can hear your own blinker on, do you ever notice whenever your blinkers are in sync? I notice things like that. But if you're in the situation where, wow, your blinkers are in sync for a little while, but then because they're off just a little bit, then they really start to differ and they're not blinking at the same time at all. And then they get back in sync as a little time passes and they're blinking at exactly the same time. And oh, they get off just a little bit. And anyway, things like that fascinate me. And it makes me think about differential equations, makes me think about these interesting results, phenomenon of beats and pure resonance. Okay, let's add one more level of complexity to our spring mass systems, and this will be the most realistic model that we've constructed yet. Here we're going to look at driven motion with damping. Remember, driven means that we have an external forcing function. This simply means we're dealing with a non-homogeneous differential equation. Now we're going to have damping. That means our damping constant is non-zero. In real physical systems, there is always some damping. This can be from frictional effects, if nothing else, or air resistance, or shock absorbers. anything that resists the velocity of that mass. In this case, the complementary function x sub c, as we have learned, may take one of the following forms. Now remember, x sub c is the solution to the corresponding homogeneous differential equation. So we're going to look at this complementary function and the three different cases that we've studied so far. Now, if our roots of the characteristic equation are real and distinct, then our complementary function looks something like this. C sub 1 e to the r1t plus c sub 2 e to the r sub 2t. If you'll recall, this was the overdamped case. That is, the mass will settle back to its equilibrium position without any oscillation. The second possibility is when we have a repeated real root of our characteristic equation, then our complementary function looks something like this. Now, do you remember which case this was? This is the critically damped case. That means there's just enough damping to stamp out the oscillation. However, it may oscillate through its equilibrium once or twice before settling down permanently to equilibrium. The last possibility is when we have complex conjugate pair solutions and our solution takes on this nature. This one's the most interesting in my opinion. This is the underdamped case. If you'll recall, the mass oscillates between two exponential envelopes before settling down to equilibrium position. So the overdamped case goes straight to equilibrium. The critically damped case may pass through equilibrium once and then settle down, maybe 0 times. And then the underdamped case, there is exponentially decreasing amplitude with your oscillation, and then it settles down essentially to equilibrium position. In each of these three cases, as t approaches infinity, x approaches 0. So all three of these cases settle down at equilibrium. And I'm thinking of equilibrium here as the 0 position or the t-axis or a horizontal axis. All of these are simply our complementary function, right? So we'll say as t approaches infinity, x sub c of t becomes the transient solution. That is, it's eventually going to be negligible. While the particular term, x sub p of t, this will eventually become our steady state term. So you'll even see your book rewrite it as your steady periodic term or your steady state term. Remember, this only occurs with damping. In the absence of damping, the mass never settles back to its equilibrium like it does with damping. So the x sub p and the x sub t interact indefinitely when there's no damping. But when there's damping, x sub c eventually goes away and x sub p takes over as the long-term behavior of the spring. Let's put all this information together and work through example 2. Interpret and solve the initial value problem 0.2 x double prime plus 1.2 x prime plus 2x equals 5 cosine of 4t. X of 0 equals 1/2 and x prime of 0 equals 0. So here we have a linear differential equation with constant coefficients, and it happens to be non-homogeneous. So we could assume in this problem that the mass of the object in oscillation is 0.2, our damping constant is 1.2, the spring constant is 2, we have an external forcing function with an initial amplitude of 5 and a frequency of 4. Now, the position of the mass at time 0 is positive 1/2, so it's half of a unit below its equilibrium position. And the initial velocity is 0. That means we're going to pull the mass down 1/2 of a unit below equilibrium position, and we're just going to release it with no added velocity. So to solve this differential equation, we're going to start on step 1, and let's find our x sub c term. That is, we're going to solve the corresponding differential equation 0.2 x double prime plus 1.2 x prime plus 2x equals 0. Now, before I turn this into a characteristic equation, I think I'm going to divide everything through by 0.2. So we have x double prime plus 6r plus 10 equals 0. So our characteristic equation then is r squared plus 6r plus 10 equals 0. This one will not factor, so let's go ahead and apply our quadratic formula. Negative b plus or minus the square root of b squared minus 4ac, all divided by 2a. So simplifying our radicand there, it looks like we have 36 minus 40. So we have a radicand of negative 4. Evaluating that radical, of course, we get 2i. And let's reduce. Our two roots are negative 3 plus or minus I. So from this, we can define our complementary function x sub c of t as e to the negative 3t, make sure you use t, not x there, times c sub 1 cosine of, the coefficient of I is 1, so we just need a coefficient of 1 here, plus c sub 2 sine of t. So this is our complementary function, or our transient term in this case. Also notice, because of the nature of this solution, this is our underdamped case. So the mass will naturally oscillate between two exponential envelopes until it eventually settles back down to equilibrium. I always think that's the most interesting case, so you knew I was going to pick an example with that, right? Let's go ahead and find our particular term x sub p. I'm going to use the method of undetermined coefficients. We're going to let x sub p match the nature of our non-homogeneous term, which is a cosine of 4t. Now, do observe in this problem, x prime is present. So if I think about the derivative of cosine of 4t, it's going to be, of course, sine of 4t, or a multiple of sine of 4t. Because that term, that derivative, is linearly independent from cosine of 4t, and I have that first derivative present, this time I am going to have to account for the possibility that x sub p does have a sine function. Okay, remember we left this off previously because we were missing our x prime term. We were just taking a shortcut there. Don't forget also, you've always got the option of variation of parameters if you like that better. Let's find our derivatives. We'd have negative 4a sine of 4t plus 4b cosine of 4t. There's our first derivative. Second derivative, xp double prime, is going to be negative 16a cosine of 4t minus 16b sine of 4t. Okay, so we're going to sub this into our, I'm going to use the simplified differential equation. So sub into x double prime plus 6, that's supposed to say x prime over here, x prime plus 10 equals 0. Now, I don't think I'm going to be able to fit all this on one line, so I'm going to work this vertically this time. I'm going to take x double prime and I'm going to add 6x prime down here on the next row. So multiplying x prime by 6, I would end up with negative 24a sine of 4t. Remember, we're multiplying by 6. 24b cosine of 4t. And I'm going to add this to, oh, missing an x term over here too. Add this to 10x. That's going to be 10a cosine of 4t plus 10b sine of 4t. Okay? Supposed to be working on the non-homogeneous equation. I hope y'all are paying attention. Okay, so I'm going to add this together and set this equal to the right side, 5 cosine of 4t. Okay, so adding our cosine terms here, we're going to have to work across. Our new coefficient would be negative 16a plus 24b plus 10a cosine of 4t. I'm going to add this to my sine terms. That's going to be negative 16b minus 24a plus 10b sine of 4t equals 5 cosine of 4t. Okay, so the coefficient of cosine of 4t on the left here is negative 6a plus 24b. That's going to be equal to the coefficient of cosine over there on the right. Okay, working on the coefficient of sine of 4t, we have negative 24a minus 6b. That's going to be equal to the coefficient of sine of 4t on the right. And because there's a missing sine of 4t, we'll go ahead and set that equal to 0. Now you can solve that system by any method that you want. Just typed it into my calculator and reduced the matrix to obtain the value for a, which is negative 5 over 102. And the value for b, which is 10 over 51. So our x sub p term, our particular term then, is a, negative 5 over 102 cosine of 4t, plus b, that's 10 over 51 sine of 4t. So those are the two parts to our solution. X sub p is going to become our steady periodic or our long-term solution. Now we do have a couple of initial conditions to consider, so let's work on those next. Putting our two solutions together, we can obtain our general solution. And this will be x of t equals e to the negative 3t times c sub 1 cosine of t plus c sub 2 sine of t plus our particular term, that's negative 5 over 102 cosine of 4t plus 10 over 51 sine of 4t. Okay, this is going to be a lot of work, but here we go. We're going to need our first derivative because remember we do have an initial condition involving our first derivative. So looking at this term, we will have to apply our product rule. So I'm going to take the first function, e to the negative 3t, times the derivative of the second. That's negative c sub 1 sine of t plus c sub 2 cosine of t. Now we're going to add the derivative of our first function, negative 3e to the negative 3t, and we'll keep this second part the same. Next, we're going to differentiate term by term here. The derivative of cosine is negative sine, so multiplying this by 4, we'll get 10 over 51 sine of 4t. Derivative of sine of 4t is 4 cosine of 4t, so we end up with 40 over 51 cosine of 4t. Applying our initial conditions, x of 0, this was given to be 1/2. So I'm going to plug 0 in for t and set the entire function equal to 1/2. Remembering that e to the 0th power is 1. Cosine of 0 is 1. We end up with c sub 1, and sine of 0 is 0, so that term goes away. Then cosine of 0 here is 1, so we have minus 5 over 102, and sine of 0 is 0. So we can easily solve this one for c sub 1. Adding 5 over 102 to both sides gives 28 over 51 for c sub 1. Okay, our second initial condition here, x prime of 0 was given to be 0. So I'm using this second equation, setting the entire thing equal to 0 and plugging 0 in for t. Remembering that sine of 0 is 0, we lose this term. Cosine of 0 is 1, so we get a c sub 2 here. Notice here we have minus 3 times 1, so I do have to consider this coefficient. Cosine of 0 is 1, so we get c sub 1. Sine of 0 is 0, we lose that term. We're going to lose this term. Plugging 0 in right here, we have 40 over 51. I'm going to go ahead and move the 40 over 51 to this side. Our goal is to find C sub 2. Recall we found C sub 1 on the previous step, so here we have minus 3 times 28 over 51. Let's see, I'm going to reduce here and add 28 over 17 to both sides. And that's going to give us 12 over 17. We are now ready to express the particular solution. Following the pattern here of our general solution, we have x of t equals e to the negative 3t times c sub 1, that's 28 over 51 cosine of t, plus c sub 2, that's 12 over 17 sine of t, and our particular term, minus 5 over 102 cosine of 4t, plus 10 over 51 sine of 4t. So to analyze the motion of the mass, we have to recognize that this is now our transient term. The mass will begin oscillating according to the natural physics of the spring. We can recognize that omega naught here is 1, and the mass will oscillate between two exponential envelopes and eventually settle down to equilibrium. Now, while this is happening, it is still being affected by the external forcing function. But over a long period of time, as my transient term goes away, levels out at 0, this becomes our steady state solution. So the external forcing function will take over in regulating the oscillation of that mass. We can see here that the frequency is 4, or we could say the period is 2 pi over 4 or pi over 2. We could also see that the amplitude, which previously we called c, would be the square root of, we want to get specific here, 5 over 102 squared plus 10 over 51 squared. That's a bit difficult to read, so let me approximate it here. We will say approximately 0.2, and we weren't given initial units. So looking at this as A and looking at this as B, recall that we can condense those into a single cosine wave with amplitude C equals A squared plus B squared. So this is probably the most interesting case of driven motion with damping. We had our underdamped case in combination with not only damping but an external forcing function as a harmonic oscillator. Now, this completes our study of linear equations with constant coefficients, both homogeneous and non-homogeneous. We really focused on the spring mass application. Even though that's a very simple physical setup, it relates to all kinds of mechanical systems. In this section, you also learned about beats and resonance, which are universal in their application to mechanical systems. Now, later in this chapter, we're not covering it in class, but if you're interested in looking ahead, there are some other interesting physical situations that if you're a mechanical engineer, you might be interested in learning about. One is one single blow applied to the base. How does that affect the motion of the mass? For example, if I strike this with a hammer once, I can program that in as a sudden, very large blow to the base, and it's going to drive that base down, and then it's going to allow that mass to have a steady state oscillation eventually. So that's in there. Also, you can look a little further into the chapter for step functions where you turn on the external oscillating and then you turn it off, and then you turn on the external oscillator and you turn it off, and you look and see how does that affect the mass over time. So as you turn on the external oscillator, it causes it to oscillate, and then it's going to settle down into its natural oscillation, and then you turn it back on, and then you turn it back off. All of that is there available at your fingertips if you're interested in looking more into these simple systems with all kinds of applications. Later on in this class, when we look at systems of differential equations, this very setup that we have looked at, we are going to complicate it a little bit more. Instead of just a single mass, we'll look at having several springs connected, and we'll look at how the individual masses oscillate. We'll model that with a system. And even though the physical experiment is very simple, that could be used, for example, to model the oscillation of floors in an earthquake. So what you're learning here is universal, and it transfers to all kinds of mechanical systems. So I hope you've learned something and enjoyed this section. Good luck on your Chapter 2 exam.